networks and learning systems, IEEE transaction on artificial intelligence, IEEE transaction on multimedia, IEEE transaction on medical, etc. And many top tier conferences such as WACB, IJCNN, ICONIP, ICIP, ICASP, EMBC, ISBI, etc. He has also served as technical program chair, co-chair, publication chair, session chair, and committee member of several conferences of international repute such as IGCNN, ICONIP, and ICIP. He is a senior member of IEEE. He serves as an editorial board member of the International Journal of Imaging Systems and Technology, Wiley publication. So, with this much brief introduction, I would also like to add one more point. He is very much actively uh, working in the image domain, applying the deep learning and the computer vision. So you may connect with him for any suggestion or any research guidance. So with this, I welcome Dr. Deepak to the session. So
Yeah, thank you.
over to you, sir.
Thank you, Dr. Vikas, for the nice introduction. So, am I audible properly?
Yes, sir. Yes, sir. You are audible.
Okay. So let me share my screen. This is probably the second session, right?
Yes, sir. It is the second session. That is the Bayesian decision theory and the basic foundation for multiple the MLP.
Yeah. So, is my screen visible?
Yes, sir. Now it is visible, sir.
Okay, I'll make it full screen.
Yes, sir. It is in.
Yeah. So participants, I mean, can they unmute their mic, or they can only write their doubts in the chat box?
So actually, this the provision is like they can only comment or they can write their questions in the chat box itself.
Okay,
They cannot unmute.
So, okay. So I will regularly check the chat box actually during my session. So if they have any doubts, or
Yes,
else
sir.
we can also discuss all the doubts at the end of the lecture, right?
At the end of the session, yes, sir.
Yeah. So thank you very much, Dr. Vikas, for the opportunity, right, to speak something in your deep learning FDP, right? So very good morning to all the participants. So in this session, we'll be talking about something Bayesian decision theory. I'll talk about in details actually why do we need this Bayes decision theory in solving some pattern classification problem, and how to represent also the Bayes classifier in terms of different discriminant functions as well, right? So this Bayesian decision theory is a fundamental statistical approach to pattern classification. So what do you mean by pattern classification? So when I say pattern classification, it is like, so this pattern can be, or you can say sample classification problem. So the samples can be given in any form. The samples can be given either in the form of an image, right? It can be given in the form of a text. It can be also given in the form of sound or anything else, right? So it can be given in any form. So how to solve a classification problem? Classification is very simple. Given any pattern, right, of different categories, like image, text, and sound, whatever it maybe the input category is. So given any pattern, your task is to classify that pattern into any of the categories. Let's say, for example, I'm trying to classify the image. Let's say the brain MR images, right? Or let's say that is magnetic resonance images into two categories. One is like abnormal or pathological category, and one is normal category, right? So what is your job? So given any pattern, right, you have to classify, or given any image, you have to classify those images either into this category or this category. So how to solve this problem? So we cannot directly apply, right, this image into the traditional classification systems. I'm not talking about the deep learning classification systems where you can directly pass images, right, into the deep learning system. But I'm talking about the traditional classification system where we usually extract the patterns and store those patterns in the form of a feature vector. You all know what you mean by features, right? Or attributes. That basically is nothing but a representation of this image. That means we want to quantify, right? We want to extract the patterns by quantifying the patterns that whatever is present in this image. And those are known as features. And these features, what you are assuming, the kind of features which you are extracting are unique, are also important features for us. So always those kind of features, right, are quantified and stored in the form of a feature vector. Let's say, for example, I have extracted D number of features. I've extracted D number of features, and then I can have a feature vector like this. You can see over here. So this one is the first feature, this one is the second feature, and this one is the last feature. Let's say the dth feature, right? So that means I'm having D number of features, right, which is representing each and every image which is given to us. And then our goal is to classify these feature vectors or these patterns into either of these two categories, that is abnormal and normal. So now the question is how to solve this problem, how to solve a classification system, or how to design a classification system. So there are multiple ways to design a classification system, right? You might have heard about there are classification systems which are neighborhood based or nearest neighborhood based, like K nearest neighbor. There are classification systems which are decision tree based, like decision tree and random forest. There are classification systems which are probabilistic based classifier. And there are also some classifiers which are rule based. There are some classifiers which are discriminant function based. Where our job is to design a straight line or a hyperplane or a decision boundary, right? So like neural network, support vector machine are coming under this category, right? Where our goal is to draw a decision boundary which can separate the samples of the different classes. We'll talk about it, right? Our focus in this lecture lies in this particular category, probabilistic based classifier. We'll see how this probability concept is going to help us in designing the classifier, right? So yes, we know that the feature vector can have any dimension. That this D could be, right, ranging from 1 to many. But we know that one feature is not sufficient to describe any pattern. So that's why we need more than one patterns, right? So now the question is, we are having more than one pattern, that means more than one feature. How can we represent those vectors in a feature space or in a vector space, right? So let's say, for example, I'm considering a two-dimensional feature. A two-dimensional feature, right, with respect to image. You can just have a two-dimensional feature space. Let's say I'm having samples from two classes, and these are like feature vectors which are like x1 and x2, where every point is nothing but a feature vector in a. So every feature vector, right, which is nothing but representing one image, right, is nothing but a single point in a two-dimensional feature space. So similarly, if you are having a d-dimensional feature vector, so in a d-dimensional feature space, every feature vector can be represented as a point. So these are some of the samples that belongs to, let's say, this category. This is C1, this is C2, or you can call it as sometimes omega 1 or omega 2. There are different notations that are used, right, in books, in research papers. Sometimes for class it is C, sometimes for class it is omega 1 or omega 2, like that. So let's say this is omega 1, this is omega 2. So this means these are the vectors, or you can say these points represents the feature vectors corresponding to each of the image which is given to us. So what is our job here? Our job is to classify a new sample. Let's say there is a new sample given to us, right? We want to classify this new pattern either into this category or this category. So there are multiple approaches, as I mentioned. So there are nearest neighbor based approaches where you need to decide that who are the nearest neighbors of this sample, right? And then accordingly, you have to decide the class level of this test sample. Or you can also apply probabilistic based approaches to solve this problem. We'll see how probability is going to help us to solve this problem. So this is a pattern classification problem, right? So I've just taken an example of an image, but if you want, you can also take an example of text, sound, anything else, right? To see how do we decide or how do we solve a classification problem in our daily life using traditional probability theory. So let's say, for example, right? So you want to suggest something from your village. I mean, suggest to some of the students in your village to take admission in a particular institute. So what we generally look at? So what we look at is the success rate, right? Success rate of the students who are enrolled or who have been enrolled in that particular institute. And also we see the failure rate, right? And the probability of the success rate can be probability of success can be denoted as probability of omega 1. And the probability of failure can be denoted as, let's say, probability of this. Right? So you know what is the success rate, and you know also what is the failure rate of the students who have enrolled in that particular institute earlier. And now your task is to predict, right? Or your task is to suggest a student, right, whether he or she should take admission in that particular institute or not. So what we usually do, we usually apply, we have these a priori, informations. These are known as a priori probabilities, right? So based on this, we usually decide, yes, this our decision rule is pretty simple here in this case, right? If you are only considering this a priori probability, I'll talk about this later on, whether this kind of decision, whether this kind of information is sufficient to take correct decision or not, right? And what are the problems which we face if we directly take this a priori probability informations, right, to solve a problem. How to decide? This is the decision rule, right? This is the decision rule, how to take the decisions. So how do you know that whether, the student to take admission or not? So it all depends upon the probability rate, right? It is like probability, if the probability of omega 1 is greater than probability of omega 2, then we say that it is omega 1. So that means we'll talk in favor of this one. If the probability of success rate is C, then we can recommend, yes, you can just directly go to that particular institute. But what if when the classes are equiprobable? That means when the success rate is having, let's say, probability value 0.5, and the failure rate is also having probability value 0.5. So in that case, so this kind of decision rule is going to fail, right? At the same time, what it seems that making decisions by only looking at the prior probabilities is not a good thing. So that means, so it is not even logical. So instead of that, what we should look at the observations or the features which influences the success and this failure rate. This could be the quality of the faculty members they have, maybe the environment they have, the kind of facilities they are providing. So these are known as actually the observations or the additional features. Instead of only focusing on the prior probabilities, what we can do is we can also focus on the different features which influences, right, this probability values, like probability of omega 1 and probability of omega 2. So then what is our goal? In that case, what we can do is we're trying to design a more logical decision rule, right, compared to this only a priori probability based decision, right? And this is where actually this Bayes decision, this Bayes rule comes into the picture, right? So we'll talk about it. What we want to do is we want to find out this kind of probabilities, the probability of X, given, let's say, omega 1, the probability of, these are like the probability distributions with respect to, class 1, or probability distribution with respect to class 2. Instead of only computing probability of omega 1, we're interested in computing this kind of thing. And these are known as class conditional probabilities. Class conditional probability. Fine. So, but what is our goal? Goal is something like this. Given a pattern, so what is our goal? So goal is given pattern X, I mean, these are like test samples. Your task is to find out, right, the probability with respect to class 1 and your probability with respect to class 2. So this is what we want to find out here. This is our problem step. So given a test sample, you want to find out the probability with respect to class 1, and given the probability, given a sample X, right, or a feature vector X or pattern X, your task is to find out also the probability with respect to class, right? So just I will talk about how to actually find out these kind of probabilities, which are known as posterior probabilities. I will also define all these terms in a moment, right? So before that, we should also have idea behind something called as a joint probability, right? So what we exactly want to do here is we want to find out actually the probability of a sample, right? Probability of a sample that belongs to right, that belongs to let's say class I, where I is nothing but 1 and 2 in this case, because we are only considering 2 classes. So the probability that the sample belongs to a class, simultaneously, right, the sample has some features X. So this is actually a joint probability, right? So these concepts are important here to understand, right? The Bayesian decision theory, right? So this is joint probability, right? Where we are having, you can say, two different types of variables like Wi and X, which represents the class. It can be omega 1, it can be omega 2, because I value varying from 1 to 2, and X is like the input which is given to us, or the input features, the input patterns. So what do we want? The probability of a sample belonging to class I and has simultaneously some feature X. Can we define this, right? We know from our college level mathematics that it can be written in terms of conditional probability as probability of omega I given X into probability of X, which can also be written as probability of X given omega I, right, into probability of omega I. So hence, I can write probability of omega I given X, right? So I can just make them equal, and I can just make it as LHS. This is RHS. So I can just take this to the denominator part. Denominator part here. So I can simply write probability of omega I given X is equal to probability of X given omega I into P of omega I open P of X. And this formula, which you've already seen and also known as Bayes theorem, right? And we'll see how this kind of equation is going to help us in solving a pattern classification problem, where X is nothing but a pattern, can be represented in terms of X1, X2, and so on up to XD, right? XD, that means this is a vector, and this is a pattern with respect to any input data, and for which you want to find out, right, the class level, whether it is omega 1 and omega 2. Instead of computing only the prior probabilities, that is probability of omega 1 and omega 2, we are computing a posterior probability, that is probability of omega 1 and omega 2 given X, right? And we'll also have a decision rule here that yes, what is your task? So given a sample, your task is to find out the posterior probability, and to find out this posterior probability here, we need these are the terms, like this term, which we have already talked about, is known as class conditional probability or likelihood of a class with respect to a particular pattern X. This P of Wi is well known to us, which is known as prior probability, and this is a total probability, right? So these terms can be ignored because this value is same in the classes, right? So we'll see later on how can we solve given a pattern classification system or a classification problem, how to design a Bayes, a classifier to solve the problem, right? So what is the decision rule in this case? So earlier we used to see, earlier we are having a decision rule like this, right? The sample will belong to omega 1 probability of omega 1 is greater than probability of omega 2. That is the prior probabilities. But here in this case, instead of, right, finding out the prior probability, finding out the maximum between the prior probability, you have to find out the maximum among the posterior probabilities. That means if this is greater than this, if the posterior probability of omega 2 given x, omega 1 given x is greater than omega 2 given x, so you can say my x will belong to omega 1. Otherwise, x will belong to omega 2. Could you follow? So there are three terms. I told that this is a kind of normalization term over here, and this is going to be same for all the classes. So we can easily denote this term. So what are the two terms which are important for solving a classification task? Is this term, that is the class conditional probability, and the prior probability. This prior probability is the prior information, can be directly computed from the data itself. I will talk about it in detail. I'll give you implementation view of this so that you can implement this algorithm from the scratch with the help of either Python coding or MATLAB or R coding, right? Now the question is how to compute this. What is this exactly? The class conditional probability, right? So how to compute this term? So this is a probability distribution term, otherwise known as class conditional probability with respect to class 1 and class 2, and how to compute this probability distribution. What kind of probability distributions we can assume, right, in Bayesian decision theory to solve or to design a Bayesian classifier. Now we'll talk about, right, how to find out this term, right? So in the college level mathematics, you might have seen that there are different types of probability distributions we have with respect to different random variables. So we have continuous probability distributions, we have discrete probability distributions. So out of all probability distributions, Gaussian probability or normal probability distributions is the most popular one and is being used in data science, machine learning, and deep learning. And its concepts are being used in many places, right? Including, right, not only in Bayesian classifier, but also in generative models as well. So maybe there are some lectures dedicatedly designed in this particular FDP, right, for generative models, where also you will find the applications of the probability distributions, and especially, right, Gaussian probability distributions, and the concepts like joint probability distributions and conditional probability, right? So the data of a class is represented by, of course, a probability distributions where every feature can be represented as a random variable, and every random variable is associated with probability distributions, right? The data is forming a single cluster, so we can assume that yes, the data is forming, right, a single cluster like this. We can assume that the data is following Gaussian distributions, right? If you want, you can also prove it, right? If you just generate some of the random points with the help of Gaussian distribution, so you will find that those data will form a clusters, but we can't say it's safe. It can be, it can be a circle, it can be ellipse as well, right? It all depends upon the kind of variance, or the variance is especially in case of multidimensional data. We don't call it as a variance, we call it as a covariance. We'll talk about it also in a moment. Kind of, the Gaussian distribution formula which you have seen, right, is this one, right, which is sometimes known as univariate Gaussian distributions, where we usually have only one random variable or one variable, which is x. And this is how actually the distribution looks like, a bell-shaped curve. You can see over here. This is the mean, this is the standard deviation, and the most of the data points falls within this regions, right? Falls within this region. If you just change the mean value, and if you want, you can also draw this kind of graph. And what you have to do is you have to just choose the x values randomly, let's say from -10 to 10, for example, and you have to apply this formula. However, you can see, right, to what is there in the formula is there are two parameters, like one is like mean and one is like the variance. There are two parameters we have. So you have to also provide the value of the mean, the value of the variance, right? Accordingly, if you change the variance value, so accordingly the shape of the curve is going to change, right? If it is small, then obviously it is going to be like this, and if it is larger, it is going to be like this, right? So And mean value, if you want to shift, so the peak point will actually come to this mean value, right? So I mean, if you want, you can just draw it, and if you just change the mean value and the variance value and check how the behavior of the curve is changing with respect to the value of mu and sigma square. Mathematically, we denote this normal distribution or Gaussian distribution in this way, right? So where mu is a parameter, so this is like standard deviation for us, and we sometimes use n over here. Fine, but this is only for one particular variable. But as I mentioned, we have to deal with for a pattern classification system, we cannot have only one feature. We'll be having multiple features. So that means this x will have more dimensions. We can't have only one-dimensional value or one-dimensional variable, right? We can't have one feature which can represent all possible patterns. No, that is not possible. We'll be having multiple values, right? In that, so we can't apply this kind of formula right here to find out this value. Is that correct? So we'll be having something called as multivariate Gaussian distribution formula, and this is how the actually formula in case of multivariate Gaussian distribution looks like. I'll discuss in detail what are its terms, how to compute these terms, and how to also find out this. This is known as probability. I mean, here it is just like a probability distribution function, but if you want to make it, class conditional probability, I will also tell what you have to make changes in this equation. Fine. So one more also interesting thing I would like to discuss here, that you can see in this particular example, I have a lot of samples, two-dimensional samples. Especially when I say two-dimensional samples, what does it mean? That means every sample is represented with the help of a two-dimensional feature vector, right? Two-dimensional feature vector, so that I can easily plot it in a two-dimensional feature space. So, and these are the samples that belongs to, let's say, class 1. These are the samples that belongs to class 2, and these are the samples that belongs to class 3. Fine. And one thing I can highlight over here, that yes, class, right? Each class is its own mean, probably somewhere here, maybe somewhere around here. If you want to find out the mean, it is very easy to find out the mean, right? So you are given a set of samples. You are given a set of samples, let's say, having only two features, x1 and x2, having different values, say 0.5, 0.75, 2, 3, like this. You can just easily find out the mean vector over here. So x is like a two-dimensional vector over here, right, containing two different features, and every point is nothing but a vector here. So it belongs to a particular class. For every class, you can find out the mean, and for every class, you can also find out the variance. And you know what do you mean by the variance? It's basically the spread out, right? The spread or the dispersion of these data points with respect to its mean. That's what is the variance is all about. But we can't directly compute, right? I mean, we can't directly use the variance value over here. So to find out the variance in case of random vectors, right? In case we know what do you mean by random variables and random vectors. The collection of the random variables are known as random vectors. So in case of random vectors, we'll be having something called as a covariance matrix in place of only variance. Covariance matrix. I'll talk about it, how to compute covariance matrix and how it is going to help us. Yeah, these are the reasons actually, of why actually Gaussian distributions has been widely used in pattern recognition, machine learning, deep learning, and everywhere, data science and all. This is only because of the mathematical tractability and the central limit theorem. Please go through it. Central limit theorem. It is even written over here, right? Okay. So our main goal, as I mentioned, is to find out this particular term, right? Because we know how to compute this term. Only we need to find out this term, right? When x is a multi-dimensional vector, not a single dimensional vector, right? So to find out that, we have something called as a multivariate Gaussian distribution formula. I've just modified something over here. So previously it was a single value, the mean was a single value, but now this has become a vector. And here C is sometimes also written as sigma or S, which represent, these are different notations you will find in different research papers or in different books, right? So I mean, to represent the covariance matrix, we'll talk about it. What is a covariance matrix and what are the properties of a covariance matrix as well, right? If we look at this formula, it looks a little bit similar to the to the formula which you have seen earlier. right? For one-dimensional, or you can say univariate Gaussian distribution. But here, everything is a vector or matrix, not a single value. So fine. So 2 pi to the power d by 2, where d is nothing but the dimension of the feature vector I've already mentioned, right? So for simplicity here, I'm considering, d is 2. That means a 2-dimensional feature vector. It could be even d-dimensional. That means 5-dimensional, 10-dimensional, even 100-dimensional. But yes, for simplicity, we have taken x as a 2-dimensional vector, right? So either we can represent, the features in the column representation, the column vector representation, or in the row representation. So accordingly, there will be slight change in the formula as well, right? So here in this case, actually, the x is represented in a column representation, but we usually follow the row representations, right? So I'll also tell if I want to represent x in a row vector representation. So what changes I have to make over here? Fine. Now you look at here, so it is d by 2, and then this is particularly, the c is nothing but a matrix over here, and this denotes the determinant to the power 0.5. Then it is e to the power minus 0.5, x minus mu transpose c inverse and x minus mu. We don't know what is the size of actually c till now, but what do we know? That x is having size, right? Here in this case, actually 2 cross 1, but you are just taking the transpose to make it 1 cross 2, right? So this has to be, this x is, let's say, right, after this transpose and all, right? So this is like this same size mean vector you will also get. I've already shown you, right? So here in this case, so the size will remain same. If it is 1 cross 2 here, this one also will be having 1 cross 2. So we can easily subtract one from another here, one from another, and ultimately after this transpose, what you will get is a 1 cross 2 vector. And now, how to compute this, covariance matrix? I will tell a moment after. So, but let's say writing the size of this covariance matrix is always d cross d, where d is nothing but the dimension of the feature vector. I'll talk about it why actually it is d cross d, and why it is always the square matrix, and whether it is having other properties as well. And finally, this is like 2 cross 1, because you can see over here, x is by default represented in a control vector representation. So it is 2 cross 1 minus mu is also 2 cross 1, right? Here you can see it is 2 cross 1. So 1 cross 2 into 2 cross 2 will give us 1 cross 2, and then into 2 cross 1 it will ultimately get a single value. So e to the power, obviously it should be a single value. So that you need to take care that e to the power minus 0.5 into a single value, right? So you have to represent, either you can represent x in the form of columns or in the form of rows, it doesn't matter, but it ultimately should give us, right? The dimension has to match properly, and it has to ultimately give us a single value, right? So e to the power single value, it is very simple, right? To get the values for any x, we can easily find out these values, fine. Now I'll talk about how to actually compute the C matrix over here. As I mentioned, is a covariance matrix and how it looks like. And then how to find out, actually, we want to find out this, right? Probability of x given W1, probability of x given W. These are class conditional probability or likelihood of a class with respect to this x, right? So what changes I have to make over here? I've already mentioned that every class is having their own mean and own covariance, right? So that means what changes I have to make actually while computing this, right? I have to only make changes. So in the, let's say I want to find out P of x given W1. That means I want to find out the class conditional probability here with respect to class 1. So what changes I have to make here is I have to change this C by C1, mu by mu1, because the mu and this, I've already told that yes, the variance as well as the mean will differ from class to class. This is what the changes you have to make, right? So if you want, I can also make it generalizable. So it will be x omega I. I can just make it ci mu I, ci inverse. This is a matrix inverse, right? This is a matrix having size 2 cross 2, and if you also take the inverse, right? So this is going to be 2 cross 2 as well, and this is right mu I. Fine. So it is mu I, it is ci, and if I is nothing but 1 and 2, which are like class 1 and class 2. Hope you got my point. How to get these values, right? Once You compute these values, and you are having, you have already got something called as a prior probability. You can just multiply these two values, and what you will get is the posterior probability value. Based on the maximum probability value, maximum posterior probability values, you can decide whether the sample belongs to class 1 and class 2, right? So this is a more logical one compared to the earlier one where we only focused on the values like prior probability values. Now let us look at how to compute and how it looks like, especially like the covariance matrix. You see how the covariance matrix in case of a two-dimensional feature space looks like. It looks like this, right? So it's a matrix having size 2 cross 2, as I mentioned, always having size d cross d if you are having, right, d cross, d-dimensional feature vector, fine. So what are the, if you look at the diagonal elements, these are like simple variances with respect to each feature, sigma 1 square, sigma 2 square. You can compute these values. Let's say you are given a set of samples, right? Let's say these are set of samples given to us, like the first sample, second sample, third sample, and so on. So you can, if you want, you can also find out the variance of this, and what is the other parts. Other parts are like the relationship between x1 and x2, right? And x2 and x1. Relationship between x1 and x2, which is sigma 1, 2, and the relationship between x2 and x1. That means you are trying to find out the correlationship between, right, the two different features which is given to us. And if these values are 0, that means the features are independent or the features are not correlated. They are uncorrelated, right? So how to find out this? We know the formula from the school level mathematics, that how to find out the sigma square, sigma 2 square. Yes, you can easily use this formula which you have already learned from your college level mathematics. And this here E is nothing but the expectation value. That's the mean value, right? You have to compute the variance using this formula in this case. And for these two cases, you have to find out the variance in this way. Expected, right? Expectation of x minus mu1 into x minus mu2. And one interesting properties it is having is, of course, a square matrix. It is also symmetric in nature. That means the relationship between the correlationship between 1 and 2, feature 1 and 2, is also same to the correlationship between feature 2 and 1. So that's why these two values are going to be same, and this matrix is going to be symmetric matrix. Right? This matrix is going to be a symmetric matrix. So it's a square symmetric matrix. Also, it is a positive semi-definite matrix. We'll talk about it later on. What do you mean by this positive semi-definite matrix, right? Well, I mean, if you want to find out the eigenvalues of this particular matrix, so it is going to be, positive values, 0 and positive values especially. I mean, you will not get any negative eigenvalues if you want to find out on the eigenvalues from this particular matrix. Then how to directly compute? So if you want, you can also compute, every element of this particular matrix individually by using this formula. If it will be, right, if it will be a three-dimensional one, then if you have to just extend it to sigma 1, 3. Similarly, it is sigma 2, 3, then sigma 3, 1, sigma 3, 2, then sigma 3 square, like that. You can also modify the formulas over here, and you can individually compute these values. But if you want, you can also directly use a formula, right? Okay, this is how actually bivariate Gaussian distributions looks like, where we are having a two-dimensional data, and if you want to print a Gaussian distributions, right? I mean, basically the graph for Gaussian distributions, when the data is two-dimensional, then it will look like this, right? Fine. Yeah, this is the formula which you can apply, through which you can directly compute the covariance. You can easily know. So what I'm trying to do here is we are giving a data. Let's say having a lot of samples. X1 and X2 are the two features. We are having samples here, samples here. So what we are trying to do here is having, let's say, size in general. Every vector is having size 1 cross d. That means there are x1, x2, and so on up to xd number of features. I hope you got my point. And as I mentioned, the covariance matrix will be having size d cross d. So what is this formula saying? That what we are trying to do here is xi minus mu. That means we have to find out the mu vector here. That means obviously we're trying to do the same thing. That means we're trying to find out the distance, right, from the mean. It's very similar to the variance formula which you've seen, but we are right now talking about the factors, not the single values. So mu will also be a vector having size 1 cross d, right? So what I'm trying to do here is xi is nothing but 1 cross d. Xi is the first sample. So we're trying to find out the difference between each samples. That means xi, I mean, here it is like the first sample. So this minus this will be 1 cross d. The transpose will be d cross 1 multiplied by, again, 1 cross D minus 1 cross D, it is 1 cross D. So for first sample, and then you will multiply them together. So what you will get is a D cross D matrix for the first sample. Then there is a summation outside, right? So what you have to do, you have to repeat the procedure. You have to find out the D cross D matrix. You have to find out the difference again from X2 to mu transpose, then XY minus mu. Again, you will get a D cross D matrix. So you will get, let's say I'm having n number of samples over here. So for every n number of samples, you'll get a D cross D matrix. You will add them together, then divided it by n minus 1 or n. There is a difference actually why we're, by applying n minus 1. If you want, you can also take n, but there is a difference, right? In general, we usually take n minus 1 here. Fine. So this is a formula. I mean, you have to add all those matrices, right? With respect to x1, x2, and so on up to xn, and then divide it by n minus 1. And then ultimately you will get a D cross D matrix where every element is nothing but where the diagonal elements are nothing but the variances and the others are like covariance values. I mean basically the correlationship among the features, right? So this is the formula which can be easily implemented with the help of a for loop over here. Fine. If this kind of question is given to us, I mean if the question is to compute the Gaussian PDF for the Gaussian probability distributions. For a particular sample, let's say x1 and x2, sorry, this is x2, this is not x1. For these two samples where mu is given to us, and because we are dealing with a multidimensional data, so then of course there is a covariance matrix given to us, which is 1001 in this case. So that means this is a covariance matrix C of sigma, and mu is a mean vector. So what is your job is to, let's say, find out the Gaussian PDF, or basically the PDF, right? Or you can say the class conditional PDF. So how to compute it? So you know the formula. So you have to, let's say you are dealing with right now probability of x1. So what you have to do is, in case of x1, so what you need to do is only mu is given to us, C is given to us. Only you have to replace x by x1 and find out the value, right? So I know you can easily do it, right? It's not 8% of like assignment. So if you want, you can just do it and check whether these values are correct or wrong. So I'm not sure whether these values are correct or wrong. So please check, right, whether you are getting similar values or not by applying these things. So why actually I've kept this particular problem? Because if you can solve this problem, you can easily implement, right? So that you can easily know that what should be the dimension and how to match the dimension so that ultimately you will get a single value over here, right? So that's what you need to focus on here. So now we have seen that how to compute actually the class conditional probabilities. That means to solve or to design a Bayesian classifier, what we require is, for simplicity, let's say we're trying to solve a binary classification or two-class pattern classification system. And for that, we have two classes, class 1 and class 2. And we know that, yes, we have to compute two posterior probabilities, like probability of omega 1 given x, probability of omega 2 given x. So what it says, given any new pattern x, we want to find out its probability with respect to omega 1 and omega 2. And if which the probability is the maximum one, we can accordingly assign the class level. And you know that this can be easily written as this probability of x given omega 1, which is just now we have seen, can be computed directly from the multivariate Gaussian distribution formula, right? By only changing the mu value and the sigma value, which is usually different from class 1 to class 2. And this is the prior probability values, which is already given to us. From the data itself, you can find out that how many samples that belong to class 1, how many samples that belong to class 2. Accordingly, you can find out the prior probabilities. As I mentioned, this is a normalization factor known as total probability. So we can easily, ignore this one. So to only take the decisions, we need these two terms. These terms can be easily computed. This term, for this term, we need to only apply that formula, nothing else. And this concept can be, this concept can be easily extended to a multi-class classification problem, because this is this is actually the value which we have computed for two-class classification system. And for this two-class classification system, the what I can say that the decision rule will be like this. I have already discussed the decision rule, right? And this is known as the Bayes decision rule, right? So where if the probability of omega 1 given x, these are the posterior probabilities, and posterior probability of class 1 is greater than posterior probability of class 2 with respect to class 1, then we can assign, right, our x to omega 1, right? Because this is greater. And as I mentioned that this approach, this rule can be easily extended to multi-class classification problem. So in that case, I can have a generalized rule like this. So X can be assigned to any class, right? It can be, I value here can be 1, 2, 3, 4, 5. So for every class, you need to find out the posterior probability value and the class for which you are getting the maximum posterior probability value. You have to assign your sample, especially the test sample, to that class for which the posterior probability is the maximum one. So this is the generalized rule, right? Where J is not equal to I, that means J and I are two different classes over here. And as of X is the normalization term, right? So normalization term, so finding out this posterior probability is also equivalent to finding out the class conditional probability multiplied by the prior probabilities. I hope it is clear. And here is an example given to you. And if you want, you can just solve this problem and check whether you are getting this output or not. So what is this problem? So you are given a two-class classification task over here, and where the two classes are represented as omega 1 and omega 2, and they are following the data of both the classes are following Gaussian distribution. This is the assumptions we are making over here for designing a Bayesian classifier, right? And then, as I mentioned, that for every classes, there'll be for each class, the mean, there'll be some mean, there'll be some variance. Here in this particular scenario, the variance or the covariance is same for all the classes. That is C1 and C2 are nothing but the two covariance matrices. It is like sigma 1 and sigma 2, and both are same. But mean is different. The variance could be same, but mean must be different, right? So this is given to you. Everything is given to you, and you are also given that the classes are probable. What is this? These are like prior probability values. So what is your task? Your task is to classify a sample, a new sample, either this omega 1 or omega 2. So what you have to do? You have to compute the posterior probability. With posterior probability with respect to class 1, posterior probability with respect to class 2. So what you have to find out? You have to find out these values. Only two values. This is already given. This value is already given, which is 1 by 2. 1 by 2 in this case. If you want, you can also ignore this term because both are same positive values. And if you can ignore this term, and if you can find out this class conditional probability, which is nothing but a multivariate Gaussian distribution, then you can easily check that the posterior probability, is maximum for which class. I hope it is clear. Is there any doubt? Can you compute this or can you solve this problem? Because if you can solve this problem, you can extend it to, if you are given a data set, then you can easily implement a Bayesian classifier. For which, in that case, I will tell that how to compute this mu1 and mu2, C1 and C2. But in this case, it is given to you. So can you just compute, the class level for this test sample? You see, this is a test sample for which you are trying to find out the class level, right? Everything is given to us. These are like parameters here. It is given to us. And you have to only put these values in the formula, which I've already shown you, multivariate Gaussian distribution formula, to find out this term. You have you are given these values, prior probability values. Only you have to multiply them together. Then you have to check that whether you are getting this kind of values or not. So here in this case, what I'm getting is probability of omega 1 is greater than probability of omega 2. So that means based on this rule or Bayesian decision rule, I can say my X belongs to omega 1. That means X is classified to class 1. There's one property also you can see over here. If you just check, the class, this particular sample, and this particular sample is close to this mean compared to this mean. I'm having two classes over here, right? And my sample is near, my sample is somewhere over here, the new samples. And this is, let's the mean of class 1. And this is, let's say, the mean of class 2. So what I'm trying to say here is my sample is close to the mean of omega 1, and it is far away from the mean of this. In that way also, I can, right, under these situations, I'll talk about it later on. So under these situations, I can say that this Bayesian classifier can also be, simplified to minimum distance based classifier, which is a Euclidean, classifier. So where in that case, what you can do, is you can simply find out the distance between X to the mean, right, of each class and find out the distance, the minimum distance, right? Here in this case, the distance from, I mean, if you just try to find out the Euclidean distance, right, between X and mu, so you'll find the distance, right, D1 is smaller than distance D2. So D1 is like the distance between X and mu1, and D2 is the distance between X and mu2, right? So, I mean, if D1 is less than D2, what does it mean? That yes, the distance, that X is closer, my sample is closer to the mean of class 1, that means it should also, I mean, it should belong to the class 1. This is how actually we classify, right, with the help of Bayesian decision theory. I hope it is clear. If you are having any doubts, so you can just write your queries in the chat box. Then I'll move on to the next part, which is a discriminant function. Little bit mathematical, but very interesting as well. Yes, because sir, okay. So is there any? You can see. Is there any comments? Or
Sir, right now there is no comments. No questions are there. So, participants, if you have question, you may ask, or else the sir may continue. Sir, we may continue, sir.
Okay. So here, this slide basically I've kept intentionally. I mean, how to solve and how to implement this particular, classifier given a set of training samples and testing samples. Let's say if it is even not given to you, so you can just how to divide a data set into training and testing, and then from where you have to find out the parameters, like the parameters. What are the parameters required? Like for simplicity, I have taken here there are two classes. For every class, you will get a mean vector, and you will also get a capital C1, and there are two matrices, right? These are like two covariance matrices with respect to each class, right? Similarly, if you want, you can also find out probability of omega1, probability of omega2. What are these? These are like prior probability values. How to compute? Let's say, right? Let's say I am considering a very ideal data set. I mean, well-balanced data set, you can say. Having 100 samples, 50 from each class, or all samples are having 4-dimensional feature vectors. That means features. And I'm following the 70% and 30% split ratio here. Of course, I'm following the 70% and 30% random split ratio, and it is stratified as well. That means I want to take 70%, not only from the whole data, but also from both the classes, which is known as stratified. Very, very important concept. Stratified is very, very important here. So stratifying the data means we have to take equal proportions from each of the classes, right? So that's why if I directly actually apply 70% over 100 samples over the whole data, I'll definitely get 70 samples, but you can't make sure that you will get 35 samples from C1 and 35 samples from C2, right? You may get 40 from one class, 30 from one class, right? So the stratified is going to help us even in case of imbalancing in the data, where the data is imbalanced. In that case, also you can apply the stratified rule, right? So we can just address that issue to some extent, right? It cannot solve the problem, but yes, we have to follow this so that the model should not be biased towards one particular class, right? So you can see over here in the train set, I'm having 30 samples from one class and the 30 samples from another class, and rest 15 samples, right, went for testing. Fine. So now the question is, what will be the value, right? What will be the value for the prior probabilities, like probability of omega1 and probability of omega2. I'm having two samples over here. I'll make it omega1 and omega2. So I have to follow the same notations actually. Omega1 and omega2. Yes. I can see. Is there any comments in the chat box? Yeah, I mean, the data set will look like this. See, the data set will look like this. The data set will look like, it will be a, yeah, there will be 100 samples, of course. So there will be 100 rows over here, right? So these are like samples 1 to 100. And there will be 4 features. Feature 1, feature 2, feature 3, feature 4. And classes are also given. Y is also given. These are X and Y is also given because we are talking about the supervised learning scenario, right? So, and out of all this, we are just, randomly picking some of the samples, 70 samples from each of the classes, right? 35 samples from each of the classes to just form it as a train set. There will be a test set, fine. So this is train, this is test, I already mentioned. So we have to build our model only with the help of training samples. That means we have to find out the parameters with the help of train set, not from the test set. So test set is only used for the evaluation purpose. So that means parameters in this case are nothing but these are the values which you need to find out. If you can find out these values, these 6 values, so then you can easily compute the posterior probability values for each of the test samples. And then you can just assign a label to each of the test sample based on the maximum probability, maximum posterior probability rule which we discussed. So you know how to compute this. So in this case, right, you can easily compute, right? So in this case, you can easily compute what is this probability of omega 1 and probability of omega 2, right? So I'll just take a 1 minute break right now, then I'll come back actually. That's because I'll just take a 1 minute break, please. Yeah. So fine. Yeah. So am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Screen. What about my screen? Is it visible?
Yes, sir. It is visible, but not in full screen mode, sir. Presentation mode is not.
Yes. Okay, I'll make it to presentation.
Yes, sir. Now it's fine.
Yeah. So as I mentioned that how to compute actually these values, you know that 35 samples in the training set belongs to class 1. You can just directly compute this P of omega 1 as 35 upon 70. There are total number of 70 samples. So you can also compute directly, it is 35 upon 70. It is like 1.5, I mean 0.5 and 0.5. That means these are equal probable. Both the classes are equal probable by looking at the prior probability. So you can't take decision directly based on this because both are equal probable, right? And find out actually this mu1 and mu2, you need to further divide this train set into 2 parts. One is like samples from class 1, the samples from class 2, and then from the samples from class 1 you have to compute mu1, From the samples from class 2, you have to compute, let's say these are samples from this, from here you need to compute mu2 and C2, you know the formula. And from here you need to compute mu1 and C1. And then you know how to compute and how to find out probability of X given omega1, probability of X given omega2. You can find out this with the help of that formula which we discussed, multivariate Gaussian distribution formula. Then you will get a value multiplied by with the prior probabilities. Then you will get posterior probabilities for a particular sample, test sample X. So similarly, you can repeat this procedure for all the test samples, and you can assign a label to each of the test samples, and then you can check the performance of the model. Right? This is how you can simply, implement a class, Bayesian classifier. Fine. So moving on to the next topic, discriminant function. I'll go a little bit faster. I think we're running out of time. So right. Discriminant functions are nothing but one of the useful ways actually to represent a classifier, right? So where you can assign a particular feature vector x to omega I, this gi of x is greater than gj of x. What does it mean? So let's say x is given to us, right? X is nothing but a d-dimensional feature vector is given to us. For the feature vector, you have to compute the discriminant functions like g1, g2, and gc, where c is the number of classes like 1, 2, and so on up to c. And you need to check, right, which one is the maximum one out of all possible, right, gx, or out of particular all g1, g2, and gc. Like we'll get the c number of actually discriminant functions over there, and you need to check this condition especially where if g of I is greater than g of j for all j not equal to I, then what does it mean? That you want to assign x to that particular class for which, let's say you can, let's say if you want to assign, you can assign x to omega 2 only if g2 of x is greater than all other g's, like g1, g2, and up to so on up to gc, right? If g2 of x is having the maximum values compared to other g values, right? So these are like any g can be a discriminant value. So then I can assign, right, this x to class 2. So in case of Bayesian classifier, this g of x can be directly taken as the posterior probability values, like it is like p of omega I given x, because we are looking at the maximum values. So the g of x, that means this discriminant function, is nothing but the posterior probability value in case of Bayesian classifier. So then next we'll see, that means we are trying to actually represent the Bayesian classifier in terms of the discriminant functions. Linear, whether it is linear or non-linear, we will see later on. So what it basically do is, does is like these kind of functions especially divides the feature space into different number of regions based on the classes and separated by the decision boundaries. That means we will see how this kind of classifiers which we have seen can be represented with the help of this kind of equations. Can we represent, right, this Bayesian classifier in terms of discriminant functions like this, wx plus p. What do you mean by or w transpose x plus p, right? You might have seen this kind of equations like mx plus c in school level mathematics, which is nothing but the equation of a line. But here this it can be it can be a line, it can be a hyperplane as well. It can be linear, it can be non-linear. We do not know, but we will see. There are different cases, right? In case of Bayesian classifier, that whether we can get this kind of boundary or whether we can draw a decision boundaries, like let's say there are some samples given to us that belongs to different classes. This is one sample that belongs to one class. This is another set of samples that belongs to, this is w1, w2. So can we draw a straight line, or you can say hyperplane in case of multidimensional data, right? To separate the samples of both the classes, which is omega 1 and omega 2, right? So we'll see whether we can represent. This is basically known as wx plus b, where w is nothing but a slope and w is perpendicular to this line, right? W is a vector which is perpendicular to this line, and b represents, you all know, that's the y-intercept, and b decides the position of the hyperplane, and w basically decides the orientation of the hyperplane, right? So we'll see whether you can get how can get linear as well as non-linear decision boundaries with the help of different cases, right? By analyzing the different cases of the covariance matrix, which is used in Bayesian classifier. Fine. So yes, the discriminant functions just now we have seen, and those kind of discriminant functions, right, can be, if you are trying to apply some functions like monotonically increasing functions like logarithmic functions over these functions, you will not find any change in the classification decisions, but there will be some simplifications. I mean, basically, for simplifications means computational simplifications I'm talking about, right? That means you can easily analyze the larger formula which we have seen. Right? If you are applying some logarithmic or monotonically increasing functions over this function, so there will be no change in the decision. Rather, you can simplify these terms easily. So then what we usually do, this is the formula which we have seen just now for multivariate Gaussian distributions. Only C has been replaced by sigma, right? So and this is e to the power something that is exponential. It's another notation, nothing else. And as I mentioned that you can use a logarithmic function over here. So if you just apply logarithmic function over g of I of x, so then this term actually, you have to just apply a logarithmic term over here. We know this term can be, right, splitted into two different terms, that is probability of xi, the probability of x given omega I into probability of omega I. So logarithmic of this into this a into b is logarithmic of probability of x comma omega I plus logarithmic of p of omega I. So now we will apply. So this is that, this is the class conditional probability. You know that larger formula which we discussed. And if we apply natural logarithmic over that formula, what we will get is these are the terms. These are the terms up to this, right? We will get from this logarithmic. I'm skipping some of the steps over here. You just try to apply the natural logarithmic over that larger formula. You will get this, right? You can easily see that, logarithmic of e to the power something, right? It is like this part can be considered as a, this part can be considered as b. The logarithmic of this part is, that logarithmic and exponential part is going to be cancelled out. And what you will have is these terms. And this is like, again, logarithmic of a is nothing but logarithm of a by b. And where this minus this, again, there is a, these two terms will be negative because it is again a into b. So that's why you can see over here, these two terms are negative over here. And this is the term, which is, this term will always be there. Now we'll see how the discriminant functions, right, will look like based on the property of the Gaussian distributions, or you can say the covariance matrix, right? So there are three, cases we have. One is like when the features actually are statistically independent. So what does it mean? The features are statistically independent means they are uncorrelated. Means in this case, this I, sigma I in this case here represents actually the covariance matrix with respect to class I, right? There are I number of classes. The I may varies from 1, 2 up to C. There are C number classes, let's say, for example, right? So this, every covariance matrix is same. That means the covariance matrix for all the classes are same, and it is a diagonal one, right? So that means it is a diagonal one, and the diagonal values are also same. So that means I can have the covariance matrix like this. If I'm considering a two-dimensional data, so my covariance matrix will be like this for all the classes. Or let's say sigma 1, and I'm considering, let's say for simplicity, two classes. Sigma 1 and sigma 2 will look like this. It is just sigma square into I, that is like 2 into 1001. So here you can see the sigma 1 2 value and sigma 2 1 values are 0. That means they are independent, they are uncorrelated. So in this case, so if you are following this scenario, and this scenario will ultimately end up, right, with a simple, right, this will end up with a simple, okay, I think, yeah, this is the formula. Yes, fine. So this will ultimately give us, actually, this is the repeated part. So yeah, so this will ultimately gives us a linear decision boundaries, right? Yeah, I think missed that part, right? So a linear decision boundary. So here actually what you will get is a linear decision boundary in this case, right? Especially if you look at actually this formula, like from this formula only we will get this linear formula. So then how to do that? As you see here. So how are the terms which can be easily ignored? So this term can be easily ignored. You can see here, gi of x is equal to this term. And if you are following this scenario, then you can just ignore this term because it is independent of I, because this sigma is same for all the classes. You can also ignore this term. What you will be having is these terms, only these terms, and this sigma I inverse. In this case, if it is a diagonal matrix and the diagonal elements are same, so in this case, actually, the sigma I inverse will be equal to I upon sigma square, right? So these two terms will be easily ignored, and this one will be replaced by sigma square. So finally, what I'll be having is like this, minus 1 by 2 sigma square x minus mu I, right? X minus mu I, this square. And this is the Euclidean distance, right? And this is my final gi of x, and there will be, yes, of course, ln p of omega I. This is the term, right, which I'll be having. So, and although it looks like a quadratic equation, because it is not quadratic actually, if I open this term, I will get obviously 3 different terms like x transpose x, because this can be written as x minus mu I transpose into x minus mu I. So I'll get 3 different terms. It is like a minus b square. So it is, I'll get 3 different terms. It is like mu I transpose into x plus mu I transpose into mu I plus ln of ui, right? So this term, although looks like a quadratic one, because it is independent of I, so I can also ignore this term. So I'll be having minus 2 mu I. I'll be having another, term obviously, minus 1 by 2 sigma square outside, plus ln py, sorry, ln py is outside, right? So what I can do here is, so I can just ignore this term. So I'll be having only one term associated with x, and the rest of the terms can be considered as a constant term. So finally, I can represent the gi of x in this case in terms of omega I transpose x plus omega 0 or omega I 0. That is in terms of w transpose x plus b, which I already discussed, right? So this leads to a linear discriminant function. Linear discriminant function. In this case also, if the prior probabilities are same, right, and you can also easily ignore this term, and in that case only you will be having this term, right? So you can, these terms can be also equivalent to a minimum distance classifier, which is a Euclidean classifier. You can see over here. Your task is to find out the distance from this x to each mean of, you can say to mean of each class, right? And the g of xi has to be maximum, that is fine, but there's a negative sign over here, so that means this term has to be minimized, right? So that's why, that is actually how we can derive a minimum distance based classifier even from the same conditions, right? So this leads to a linear discriminant boundary. Similarly, if you want, you can also derive, right, the discriminant functions for 2 of the other cases I will discuss. But let me focus on this. And what we want to do here is, let's say given a set of data from class 1 and class 2. There are, let's say, samples given to you, 2-dimensional samples given to you that belongs to class 1, that belongs to class 2. What is our ultimate goal is to design or draw a decision boundary. How it is possible? First, you have to compute this g1 of x over here, and then g2 of x. Then you have to make them equal. G1 of x is equal to g2 of x, like it is g1 of x minus g2 of x equal to 0. So you'll get a line, and that line is nothing but, and how to compute this g1 of x and g2 of x using this formula, right? And you will get just simply some equations like in terms of x, right? Wx plus b, as I mentioned, right? So you'll get 2 equations. Finally, you will make them equal. You'll get a single decision boundary, and that decision boundary will help us in deciding, or you can say, or in separating the classes or the samples of both the classes. So as I mentioned that if you want, you can find out the value, right? This is the same thing which you have written, that how to simplify this kind of conditions into a minimum distance classifier when even the prior probabilities values are same. So this is the equation, right? You have to find out the minimum, right, or distance between x and the mean of each class. The second case is like when the first case was like when the covariance matrix is same for all the classes and it is a diagonal matrix and the diagonal elements are same. But the second case is the covariance matrix is same, but it is not a diagonal matrix. It can be any matrix, but the covariance matrix is same for all the classes. So again, if you apply, I mean, if you carefully analyze this equation and what are the terms which can be ignored, like this term again can be ignored, this term again can be ignored, but here the sigma I inverse will be there. You cannot replace with this I by sigma square because these are not identity matrix, or you can say the diagonal matrix having diagonal elements are same, right? So what you can do is, ultimately you will end up with again a linear discriminant functions like this. And if you just open all the terms, you will get the terms. These are the terms which you will get, and just I have represented in terms of Wx plus b or Wix transpose plus Wiz. This is the second case when the covariance, though on the variance of the class, or the covariance of each class is same, but they are not diagonal, right? And the last case is when the diagonal matrix is arbitrary for all the classes. In that case, you will end up with a quadratic discriminant function, right? You will not get a discriminant function, linear discriminant function. That means you cannot draw a line, right, to separate the classes. You have to draw a quadratic, quadratic distance boundaries, right? So if you just go through again, right, analyzing this particular, if you keep on analyzing this particular equation, right, and check that what are the items or what are the terms, right, can be ignored in the last case, because you cannot ignore, except this term which is independent of I and all, you cannot ignore other terms, right, because other terms are like sigma I is different from all the classes, so you have to keep it, you cannot remove. So that's why you see sigma is, you will find sigma I and those terms everywhere, because you cannot remove these terms because they are different, right? I hope at least you got some idea behind right now the Bayesian decision theory and how we have developed a probabilistic based classifier, right, to solve a classification problem, whether it is a binary classification problem, whether it is a multi-class classification problem, and how to even represent those kind of classification classifiers in terms of discriminant functions. Also we have discussed, right, and we have discussed the discriminant functions and how to derive the discriminant functions, I mean, like the decision boundaries in multiple scenarios, by considering different scenarios like covariance matrix, different types of covariance matrix scenarios, right? So sometimes some of the cases leads to even minimum distance classifiers, which you already discussed. I hope you can easily implement this algorithm given a data set. Also, we've discussed the implementation view of this particular classifier, right? And you will also find its applications like based on theory, its applications you will find in some of the generative models, where you will always find the the concept of Gaussian distribution, also as well as joint probability distributions and class conditional probability distributions. Okay, so I'll stop here and I'll resume my session just after 5 minutes. Okay, if you are having any queries, I'll be happy to take. Do you have any queries? Okay, which one box? So the data is 4 cross 100 dimension. Yeah, I mean, if you want, you can represent the data either in the row format or in column format, as I mentioned earlier, right? So if you, I mean, I'm having 100 samples and every sample is having 4 rows. It is up to you that how you are representing it, right? Whether rows represents samples or column represents samples, it's up to you. Okay, so absolutely correct. So probability of omega 1 and omega 2 is equal to 2. Yeah, mean is 1 cross 4. Yes, absolutely correct. Yeah. So Dr. Bikas, so we shall stop here and start the next session after 5 minutes. Yes.
So participants, the next session from Dr. Deepak will start from 12:45. So I hope you all are there. And so there are some questions I hope sir has clarified, or if not, sir will clarify on this one. So I think this session was extended, so we may wrap up earlier. Uh, so I think sir is there. Hello, sir. So the question which Prithvi ma'am has asked, how does Bayesian classification apply to deep learning? So basically, uh, we are moving toward the base. Means you have learned the basic of how the classification will work, the conditional classifier, and this will form the basis of what we are going to learn in the multi-layer perceptron. So the basis of all the classification algorithms that we are looking into, so the basis of all of them are basically the discriminant analysis. So the next discussion that is aimed at the discriminant analysis, the perceptron function, there you will get to know how this Bayesian will be transformed into discriminant analysis and how it is related to deep learning. So the chain will be basically the chain will be established by the sir itself. Um, so hope that your question will be answered while discussing the concept on discriminant function. Okay, so sir is joining. Actually, there was just some glitch on his end. So he will be joining in just a minute. Hello. Deepak sir?
Yes, am I audible?
Yes, yes, sir. You are audible, sir.
Okay, okay, okay. Thank you. So, okay. Once again, welcome all the participants to my second lecture on Introduction to Artificial Neural Network. So, because this particular FDP's main theme is deep learning, so as you all know that deep learning architectures are based on neural network concepts. Because all the deep learning architectures are known as deep neural networks. So we must understand, right, what neural network, right, does, and what it basically does, and how it solves the problems, and what is the history of neural networks, right, from where it got started and now where we are, right. So that means it all started from the traditional maculopit neurons. I'll talk about it, and then followed by perceptron, followed by multi-layer perceptron, and what you are looking at is deep neural networks nowadays, right? So to understand actually the concept of deep neural networks, right? So we must also understand, to appreciate even the capability of deep neural networks, even multi-layer perceptron, we must also learn, right, the weaknesses of the earlier neural networks, right? So then only we can appreciate the new, especially the deep neural networks, right? So let me share my screen. Yeah, I hope my screen is visible. Okay. Yeah, is my screen visible? I'll make it full screen. And this time, yeah. Yeah, is my screen visible? Yeah, thank you, Firas. Thank you for the information.
Yes, sir.
Yeah, so let us start introduction to artificial neural network, right? I'm talking about artificial neural network. So it has inspirations from obviously biological neural network, right? So we'll try to see, how it is related to biological neurons as well. So let us, first, here are some of the acknowledgements, because I've taken some of the contents from the deep learning course taught by Mitesh Kapra. He's one of the excellent professor at IIT Madras. Fine. So coming to the history of neural network, if you go through the history, so you'll find it is indeed some rich history, and it got all started 1940 when two researchers, Maculo and Peets, proposed the first mathematical, model of the neuron, right? Now, which is known as Maculo-Peet neurons, MP neuron, right? And then you will find a lot of advancements in the field of the developments. So later, Rosenblatt found that yes, there are some issues with the MP neurons, which can only solve binary problems, which can only deal with binary inputs. I'll talk about in detail what is this MP neuron and what is this perceptron today. And probably the next lecture is multi-layer perceptron, where you will find what perceptron cannot do, what multi-layer perceptron can do, right? So yes, so no, we are talking about neural network here, nothing else. So right here it is ANN, means artificial neural network. Fine. So okay, and it is if you go to 1950s and 60s, you will find the developments. Perceptron has initially proposed to deal with some sort of real values which MP neuron cannot do, and then later it has been refined, right? And then slowly people have developed something called as multi-layer perceptron, and the most important part is the backpropagation algorithm, right, proposed by Professor Hinton and his group. You all know who is Professor Hinton, who has recently been awarded Nobel Prize this year, right? And who has also developed several deep learning architectures, starting from especially AlexNet and several other architectures like autoencoders and CapsuleNet and so many others, right? So currently we are at here, but the concept of actually CNN is not at all new. It can be tracked back to in late 80s, you can say. The very first architecture, the LeNet architecture. The LeNet is the first convolutional neural network architecture proposed in 1998. And then you'll also find several other advancement of this convolutional neural network just after 2012. So there is a huge gap actually from 1998 to 2012, there's no development in the field of convolutional neural network. But after 2012, you will find several developments, right? And this, especially you can say this convolutional neural network has revolutionized, right? So yes, so today's my main purpose here is, I mean, in this session, so I must discuss actually what was happened, right, in 1940s when what McCulloch developed, and as well as Rosenblatt, right, developed, like one is like MP neuron and one is perceptron, right? I'll talk about these two models of neural network as well as the weaknesses of these models, right? And the next lecture, I think, will be from multi-layer perceptron. And where also you will get to know about one of the popular learning algorithm, right, which is known as backpropagation learning algorithm, and which is even currently used in all the deep learning architectures, right? Whether it is convolutional neural network based, whether it is Bayesian transform based, everywhere you will find the concept of this backpropagation learning algorithm. Fine. So as I mentioned that yes, the artificial neural network has got a lot of inspirations from the biological neurons. And we all know that our brain consists of large number of approximately 10 to the power 11 number of neurons, right? Highly connected neurons, we can call it as. And every neuron has approximately 10 to the power 4 number of connections. And this neuron especially has three components like dendrites, cell body, and action. And you can see how a biological neuron looks like. This is a dendrite which takes inputs from other neurons, right? And the cell body especially storms and thresholds these incoming signals, right, coming from the other neurons. And the action is a kind of output here, right, where the output signals is passed to the other neurons, right? And synapse is just a connection, right? It's a point of contact between an axon of one cell and the dendrite of another, you can say another neurons, right? So these are some of the inspirations, right? Biological inspirations. So here also there are some important points which is written over here. That some of the neural structure is defined at birth, and other parts are developed through the learning, right? And some of the new connections are also made, and others like that. Yeah. So coming to the first, right, the neuron model, the mathematical model, right, where McCulloch and Pitts, right, have expressed the neuron, I mean, especially mathematically, right? They've given just a mathematical model of a neuron, right? This is how actually the mathematical model of a neuron looks like, which also takes some inputs here, x1, x2, x3, and so on up to, let's say, xn, are nothing but the n inputs given to the neuron, like the dendrites which we've seen. And then, right, this G is especially the sum part here, which aggregates all the information over here. And F is a function which is applied over G to take the decision whether the neuron is going to fire or not. If the Y value is 1, that means the neuron is going to fire. If the Y value is 0, that means the neuron is not going to fire. So this was published in 1943. There are certain issues with this model, and we'll see what kind of problem this kind of neuron can solve. This is just a single neuron I'm talking about, which can take multiple inputs, sum them, and then you will apply some of the thresholding operation over here to decide whether the neuron is going to fire or not. There are two important things where you can note down that yes, the input and the output in this case is binary, right? That means the input, the x1, x2, x3, which I have already discussed, like continuous in this case, right? The McCulloch neurons can only deal with binary input. That means every input, right, can have only two values, like Boolean values, like 0 and 1. It is written over here. So all these x can take either 0 and 1. So then what kind of problem I can solve, right? So what kind of problem I can solve? Yeah, this is what I've already discussed, that what G is doing and what F is doing. I'll also show you the corresponding mathematical equation of this particular neuron, which is MP neuron. So what kind of problem I can solve is that if I want to, let's say, solve, or if I want to predict whether I would like to watch movie in the INOX theater tomorrow or not, right? And if the inputs are like this, like if it is directed by Chopra, if it is, if it is an action movie or not, sick tomorrow, that means whether I'm going to be sick tomorrow or not, whether the actor is Akshay Kumar or not, like this, right? So these are the inputs which can only take the values either 0 or 1. If it is directed by Chopra, then the value will be 1. Otherwise, the value will be 0. If it is action movie, then it will be 1. If it is not, then it will be 0. Right? And what is my task here? The x, all x can be represented here in the form of 0 and 1. Only this kind of problems can be solved, but we know that we cannot solve the real-time problems with the help of these inputs. Right? So that's why it is not preferable right now. So this is one of the major concerns with TMP neuron. And the outputs are also here in terms of 0 and 1. Is that clear? That means whether you want to watch the movie, if you want to watch the movie, then it is 1. If you are not going to watch the movie, then it is 0. Right? So there are basically two types of inputs, right? The inputs can be again further divided into two types. One is inhibitory types and one is excitatory types, right? So what are these inhibitory inputs and excitatory inputs? So the inhibitory inputs are those which have maximum effect on the decision making irrespective of the inputs. What does it mean? Let's say if X3 is 1, X3 is 1 means, I mean, whether I'm going to sick tomorrow, yes, I'm going to be sick tomorrow. So irrespective of the director, whether it is action movie or not, who is the actor, leading actor or not, doesn't matter. If I'll be sick tomorrow, then I'm not going to watch the movie, right? So that means this kind of inputs are known as inhibitory inputs, and those have maximum effect on the decision-making process, right? So that means the neuron, right, is not going to be fired because he's sick tomorrow, is having value 1. Right? If I'm not feeling well, so now no matter whoever is the director, whoever is the actor, I would not be going to watch the movie. So what about the excitatory inputs? Excitatory inputs are like the other inputs. They cannot take the decisions individually, but when we combine them together, then the neuron is going to fire. Right? So initially, and this is how actually, mathematically we can express an NMP neuron. You can see over here, right? So this is again a function where g of x, this is a vector containing n number of, you can say n number of features, right? x1 to xn over here. And if you look at the equation, right, or the expression here, it is like this, right? So that means g of x is nothing but summation of all the values. It is x1 plus x2 plus x3 and so on up to xn. And how to take the decisions? As I mentioned, you have to apply a function. And that function is nothing but a thresholding function. This g of x is greater than or equal to theta, which is a threshold, then the neuron is going to fire. And if it is less than theta, then the neuron is not going to fire. Right? So if you are satisfied with the actor and director in the previous case, so that means if both the inputs are on, right? That means 1 plus 1 will be 2. That means if theta is 2, you can say I am going to watch the movie. Right? It should be minimum 2. And if it is greater than 2, then it is fine. Right? And if you are only satisfied with one particular input, then you can just take the theta value as 1. Right? This particular, I'll also talk about, right? I'll try to geometrically explain actually what exactly this NP neuron is trying to do with the help of some logic gates and all. So since the input is in the form of 0 and 1, and the output is in the form of 0, 1, 1, and in 1943 at that time, so they have been implemented actually the Boolean functions with the help of these NP neurons, right? So Boolean functions, as you all know, that there could be different types of Boolean functions, could be linear, non-linear Boolean functions, and the popular type of Boolean functions are like OR, AND, XOR, and like that. We'll see whether this kind of Boolean functions or whether all Boolean functions can be implemented with the help of NP neuron or not. Right? So this is just a concise representation of the NP neuron. Here I'm just not writing here G and here F, just a theta directly I'm writing over here. Right? This is a concise representation. And we all know that yes, if G of X is greater than or equal to theta, then the neuron is going to fire. Now let us try to implement the AND function. Let us try to implement the AND function with the help of an NP neuron. How it is possible? Yes, it is possible. We all know if I'm considering a 3-input AND gate, so in case of AND gate, the output or the neuron is only going to fire if all the inputs are 1. Right? This is the only case where the neuron is going to fire. So that means in that case, the G of X will be 1 plus 1 plus 1. That is X1 plus X2 plus X3. It has to be 3. Right? Then only it is going to fire. So then the theta value has to be 3. Then only the neuron is going to fire. So now, you tell me what should be the value of theta if you want to implement a gate. Yes. Let's try to respond quickly. You can write in your chat box. If you want to implement target with the help of MP neuron, so then or function, right? So what should be the value of theta? Yes. Yeah, it's 1. Thank you. The answer is absolutely correct. It will be 1 because if any one of the input is on, the neuron is going to fire. Absolutely correct. Yes, you're correct. Similarly, you can, if you want, you can also implement NOR gate, right? So in case of NOR gate, it will look something very different because these inputs are going to be, right, inhibitory inputs, right? So these are like inhibitory inputs, right? If I take, the value as, 0 here, so this will become 1 and this will become 1 and absolutely this value will be, going to be 0 here. So similarly, if you want, you can also implement NOT functions. I'm skipping here. So now there is a question here. So can any Boolean functions be represented using MP neuron? We've just now seen, 4 types of gates. Can any Boolean functions be represented using MP neuron? Okay. Before we answer these questions, let us first try to understand what this MP neuron is doing geometrically, right? For simplicity, I have considered a 2-input OR function, and we all know that there are 4 possible inputs in case of 2-input OR function: 0, 0, 0, 1, 1, 0, and 1, 1. And these are the 4 samples: 0, 0, 1, 0, 0, 1, and 1. These are the 4 samples. And if I want, I can also draw it in a 2-dimensional space, 2-dimensional feature space. Right? I've taken 2-dimensional OR function over here. So yes, I know that the theta value will be equal to 1 in this case. And how the function will look like? The function will look like this: the g of x. The g of x will look like x1 plus x2, right? And if it is greater than or equal to 1, then only the neuron is going to fire. So what it basically tells us, that is, this equation you can derive from this particular model, MP neuron model, to implement the OR function. Now let us try to draw the equation of the line, which is x1 plus x2 equal to 1. If I want to draw this x1 plus x2 equal to 1, it will pass through this. So this is the line which tells us x1 plus x2 equal to 1. So what MP neuron is doing? MP neuron also is trying to draw a decision boundary, right? A linear decision boundary over here, where the equation is x1 plus x2 equal to 1. That means the line is passing through the 2 points 0, 1 and 1, 0. So then how can you decide that whether these points belongs to one category or this point belongs to another category? Yes, the points who are lying on and above the line, they belong to one category, and the points who are lying below this line, they are lying to, or they belong to another category. This is what it's doing. So this 0, 0 is 0 and rest other values are 1. We all know that there are 2 classes, which is 0 and 1. So these 3 are having values 1 and this is having value 0, right? So what it is trying to do, so that means this is exactly, the MP neuron here is exactly trying to give us a linear decision boundary based on which you can decide whether the samples belong to one category or not. This half is I'm on and above the line, one category, below the line, another category, right? So from where you can conclude that yes, MP neuron is trying to land a linear decision boundary. Is that clear? I hope you have understood the importance of this particular neuron, MP neuron, and how it helps in solving the problem. So similarly, if I want, I can also check whether it is giving us a linear decision boundary in case of AND function or not. So in case of AND function, only there will be some changes. The equation is going to be x1 plus x2 equal to 2. Why? You know that because the theta value is going to be 2, right? When both the inputs are 1, then only the neuron is going to fire. So this is the equation. If you remember, g of x greater than or equal to theta. So g of x is equal to x1 plus x2. If it is greater than or equal to 2, then the neuron is going to fire. So there are again for scenarios 0, 0, 0, 1, 1, 0, 1, 1. So for these only the output is 1, and for rest others the output is 0. So now you see, if I just try to draw this line, right, or this equation, so this is like x1 plus x2 equal to 2. And in this case, if I draw this, right, so then what will happen is, so the point which is lying on the line, they belong to one category, on and above. That means 1, 1. It belongs to, let's say, this category, the class 1 category, and these 3 belongs to another category, right? So the points lying below the line, they belong to one category, and the points lying on and above the line, they belong to another category. If you want, you can also extend, right, these 2 inputs to 3 inputs, and you can check whether it is giving, right, a decision boundary or not. But always it will give a linear decision boundary. That means the problem which is non-linear, that means where the points are not linearly separable, cannot be solved with the help of MP neuron. I hope you got my point. Like in XOR gate, so you all know that 0, 0 is 0, 1, 1 is also 0, 0, 1 and 1, 0 is 1, 1. So if I draw this, I cannot draw a single, I cannot, separate the samples of both the classes with the help of a linear decision boundary. So I must have a non-linear decision boundary to solve the problem, right? So that means MP neuron cannot solve cannot draw a non-linear decision boundary, right? And it cannot solve the problems like, we cannot implement XOR function, which is non-linear in nature. This is not a linear function, it's a non-linear function. So it can only solve linear problems. Fine. So in case of 3-dimensional data, where there are 3 inputs, in case of OR functions, you will get, a plane, a linear plane in place of a decision, or you can say a straight line, because we're dealing with a 3-dimensional data. So we'll just get a, decision boundary in the form of a plane, that is x1 plus x2 plus x3 equal to 1. And you can see over here, the points lying on and above, they belong to one category. The points below, which is 0, 0, 0, right, which is not visible over here, right, because that is on the other side of this plane, and that belong to another category. Yeah, so there are some implementation view also how to implement this. So what it seems that there is only one parameter, that is theta, you need to decide to solve a real-time problem here. But the only you can solve a real-time problem using MP neuron, which can take linear, which can take 0, 1 values as an input and 0, 1 values as output, right? In that case, what you have to do is you need to, set a theta value, and the theta value also lies from, you all know that the theta value will lie from 1 to n, where there are n number of, let's say, inputs. Or if you're considering d, so it will, range from 1 to d. So for what value of theta, you'll get, better performance. That is what is, learning here in this case of MP neuron, right? There is nothing called learning here, because you're directly getting the output over here, but theta is the only one parameter which you want to find out. So you can just, consider any loss function over here, kind of, mean square error or square error loss function, and that loss function will help you in finding out, right, this theta value. The theta value of which you are getting the loss, the minimum loss, you can choose the theta value. It is just a trial and error process, you can say, right? So through which you can get the best theta value given a data set. So that is why it is not, used nowadays, right? Because it has a lot of limitations, although it is having only few advantages, but it has several, severe limitations also. So what are the other limitations which MP neuron is carrying? What are the other limitations? The one major limitation is it cannot handle real inputs, right? It cannot handle real inputs. It can only handle Boolean data. It cannot handle non-Boolean, or you can say the real inputs. That means we can have the values, right? The X value, basically the feature value can be, in terms of real values. It's not necessary that it will be always Boolean values in terms of 0 and 1. So that means you cannot solve all possible types of problems where the values are, real. And always you need to convert the real values into its corresponding 1 and 0. Probably, and if you are doing this, if you are converting the real values to, this in terms of 0 and 1, probably you may lose some of the information. You cannot even, able to get some desired output from the model. Another limitation is you need to hand code the threshold value. I told you that how to find out the best theta value. In case of OR gate, XOR gate, it is simple to decide the theta value. But if you are dealing with a real-time data, right, so it is difficult to find out the theta value. We don't know which theta value is going to give us better result. But this theta can take only a few possible values. Depends upon the number of features you have. Right? I already mentioned it can take the values from 1 to n, small n, where n is nothing but the total number of inputs or features we have. So one of the major limitations of this MP neuron is we are treating all inputs equally. Right? That means the weight associated with all the inputs are equal. But if you want to give higher weight to a particular input, you can't give in this case because there is no weight associated with the input. I hope it is clear. Right? So there is no weight associated with the input. If you want to give more weightage to a particular input, you can't give. We'll see whether this kind of problems can be solved using perceptron or not. And another problem is it cannot solve non-linear problems. That means the problems which are not linearly separable. The data which is not linearly separable, you cannot solve with the help of MP neuron. We'll see, right, whether this kind of problems can be solved using perceptron or not. Right? So perceptron is another variant of, we can say the neuron. It's a single neuron, of course. Right? It's just a variant of MP neuron, and we'll see whether perceptron can deal with all these issues or some of the issues that MP neuron faces. And these are the reasons actually why we are not interested in solving problems using MP neuron. How can you solve? Right? Because it takes Boolean values always. It can't, you cannot give weights to each of the inputs. So then that's why we're not using MP neurons nowadays. Yeah. So perceptron was published in 1958 by Frank Rosenblatt, who's an American psychologist, right? So who proposed actually the classical perceptron, but later this perceptron has been refined and carefully analyzed by Minsky and Papert in 1969, right? And this is how actually the perceptron that proposed by Minsky and Papert looks like. You can see over here, there are inputs and weights are associated with each of the inputs. Very, very important. Right? So weights are associated with, weights has been introduced with each of the input in the perceptron model. So the perceptron model proposed by Minsky-Papert is nothing but a more general computational model than the maculopit neurons, which we discussed. Right? So the differences already we have discussed, right? So here the weights are introduced, which was not there in the MP neuron. At the same time, the input is no longer Boolean values. You can also pass real values as the input to the perceptron model. We'll see how we can mathematically express this perceptron, right? And we have also seen the mathematical expressions of the MP neurons. If you look at here, the mathematical expressions is like this. So it is summation of Wi into Xi. Right? What is Wi? Is the weight with respect to each of the inputs. Right? So we have n number of inputs starting from 1 to n. So we'll be having, right, in the equation, previously it was only summation of Xi, where I varies from 1 to n, if you remember. In case of MP neuron, we're only adding the X values. Right? But in this case, we are multiplying weights with the inputs, each of the inputs, right? And then we are summing them together. So after getting the sum, we are also applying a threshold over here, right? Again, there is a threshold here. If this value is greater than or equal to theta, what does it mean? Than equal to theta. So that means the neuron is going to fire. Right? You will get a value 1. And if it is less than theta, right, the value will be 0, or the y value or the output will be 0. And the neuron is not going to fire. So if I want, I can also take this theta value to this side, right? Theta value to this side, because what I want, that these weights are nothing but like, right? These weights, I don't want to fix these values. I don't want to take these weight values, randomly, or I will definitely take it randomly, but there must be a learning algorithm here who will help us in giving us the optimal values of these weights, right? So similarly, like I mentioned that I will be having one algorithm here which will give us the optimal values of this W. Similarly, I want this theta value has to be learned by that algorithm. So what I want to do, so I want to just include this theta value in this term. It is like minus theta over here, right? So The summation is starting from 1 to n. So let me show you an accepted convention of this, I mean, the mathematical expressions for this perception. So now you see here, I have just included the theta into this expression. What is this? It is like previously, the equation was like this, W1 x1 plus W2 x2 and so on up to Wn xn. So now the equation has become, if you expand actually this equation, you will get W0 x0 plus W2 x2 and so on up to Wn xn. So I know this term minus theta is nothing but this term. So that means here in this case, this x0 value is 1 and this W0 is minus theta. Right? So this minus theta can also be represented in a generalized way like this. So here the I varies from 0 to n, and where x0 is nothing but 1 and W0 is nothing but theta over here, and we can consider this W0 as a bias over here. And we all know the importance of this term, right? We all know that equation, right? W transpose x plus b, if I write y is equal to W transpose plus b. So what exactly actually we're trying to do here, right? So some x is given to us, some set of inputs are given to us, and y is also given to us, and we're trying to build the relationship between x and y with the help of a function, right? And this function is nothing but this kind of function. It's not only dependent on an x, but also dependent on some parameters known as weights and biases. And we all know the significance of this W and B for defining or for drawing a decision boundary. Where W defines the orientation of the hyperplane, right, in case of multidimensional data, and B decides the position of the hyperplane, and W especially is nothing but, I've already shown you, right? So if I'm having samples of different classes which are linearly separable, right? For simplicity, I'm taking, and I can just draw a straight line over here, and this is nothing but the equation of the, and where this is the line which we are searching for, or the decision boundary, right? So W is nothing but is a vector which is perpendicular to the line, right? Perpendicular to all the actually points which are lying on this line. So it can be, you can say that W is also perpendicular to this line. So W is a vector. This is what actually we are searching for. So you need to find out this W, because you don't know if which W, so you are going to get a better decision boundary. So there are some learning algorithms through which we will get this W and B together. I'll also talk about it. Right? The perceptual learning algorithm through which we can get the best W, right? Because we always start with the random W values here, and we ultimately end up with a W for which you can draw a decision boundary. And how can you draw the decision boundaries? Let's say these are training samples which are given to us. So yes, there can be multiple decision boundaries if you change the W, but initially the W will be somewhere around here, because you do not know the nature of the data initially. So initially the W can be somewhere around here, but if you choose this, the W can be somewhere around here. If you choose this kind of line, right? So you know that there will be a lot of misclassifications. So we cannot accept this type of decision boundaries because there are a lot of misclassifications. So then what you have to do is we have to change the weight value with the help of an algorithm. And that is what is the perceptron algorithm here does, that we will change this vector, or we will change this weight vector. Accordingly, you will get different decision boundaries, and we will ultimately end up with this kind of decision boundary, this kind of weight vector for which all samples are correctly classified. So that in future, if you find any kind of data, new data, let's say a new data, these are like test samples for us. So you can easily say that yes, it belongs to class 2, right? Because it is lying on the, or it is lying on the other side of the, or you can say one side of the plane, or one side of the decision boundary, right? So the goal is very simple here. The goal of the neural network is to, give us this kind of function. And we are talking about supervised learning setup here, because we have both input and output, right? And this B can be, this W0 can be treated as B, where always the input to the bias is always 1, right? So that means you can see over here, so this can be treated as a bias. Right? This input is always +1, and this is like a bias value for us. So if I want to also train, I want to learn these values along with this theta value together. Fine? Yeah. So, yeah. So then what kind of, again, we've already discussed, right, the Boolean functions and all. So again, whether perceptron can implement all possible types of Boolean functions, I mean, both linear and nonlinear, we'll see later on whether, okay, perceptron can solve these nonlinear problems or not, non-linearly separable problem or not. This is how macular-pit neuron, the expression of the macular-pit neuron looks like. And this is how actually the perceptron looks like. You can see over here, right? If the WIXI, this is the term, the new term that has been introduced. And earlier it was there, now it is there. Fine. I mean the most conventional form. Yeah. Now we'll see whether this kind of perceptron algorithm can solve linear problem as well as nonlinear problems or not. To see whether a linear problem, let us first consider one linear problem, and then I will consider one nonlinear problem. Fine. And check whether it is working or not. Yeah. So the equation, if you look at in case of perceptron, it looks different, right? So there are 4 samples in case of 2 function, or you can say 2 input or function, 0, 0, 1, 0, 0, 1, 1, 1, and these are the outputs. This is Y. And we know how to represent this. It is like W0, X0, right, which is 1 always, plus W1, X1, plus W2, X2. Right? If it is 0, so it is 0 means obviously it will be less than 0. Right? This is the condition which we know. This is the condition which we have seen. Yes. You can see over here, if WIXI is less than 0, then only it will be 0. So in that case, definitely, so WIXI is less than 0. Fine. WIXI is less than 0, and for rest other cases, the WIXI is greater than equal to 0. Right? So yeah, these are the expressions, 4 expressions I have got. And after simplifications, what I've got is this one. W0 should be less than 0. W2 should greater than minus W0. W1 is greater than minus W0. And W1 plus W2 is greater than minus W0. You see here. So one of the possible solutions after solving, this kind of expressions, you can get different solutions. So one of the possible solutions is, which satisfies all these conditions, you can also check. So W0 is, less than, minus 1. So where W2 is greater than minus W0, which is 1.1 is greater than 1, 1.1 is greater than 1. And then this W1 plus W2 is like 2.2 is greater than minus W0, which is 1. Right? These are the conditions. So if I just, if I choose these conditions and try to draw the line, right, using this, so I'll get this kind of line. So what will be the line? 1.1, it is like W1x plus W2x, right? Minus, W0 especially. The equation is W1x1 plus W2x2 plus W0x0, right? Equal to 0. This will give us the equation of the line or the decision, boundary. So W0, x0 is plus 1, as we all know. So it is minus 1. And this is like 1.1 x1. This is like 1.1 x2. So if you draw this equation of line, so you'll get this kind of equation. And if you look at this line, so the points which are on and above, right, this particular line, they belong to one category, that is class 1, and the point which is lying below this, they belong to another category. That means, yes, the perceptron is also helping us in solving a linear decision boundary problems, or helping us in drawing the linear decision boundaries. Fine. Now we'll take the same example which we have chosen, like the Excel example, right? Excel function, input Excel function, whether perceptron can solve this problem or not. Okay, yeah, here are some outputs, like this is Y, for 0, 0 it is 0, 1, 1 it is 0, right? These are the equations which we have got, right? So W0 is less than this, right? And W2, W1, W2 will be greater than minus W0, greater than minus W0. And this is the equation. See. So there are some problems with these equations, right? So, I mean, there are some inequalities here, which is not valid, right? So you will not be able to find a solution which will satisfy all these criteria. So that means you cannot solve this kind of problem with the help of perceptron, right? Because you cannot solve these inequalities. You cannot solve these inequalities to ultimately end up with a solution, right? Because some equations contradict some other equations, right? So W1 is greater than minus W0. W2 is greater than minus W0, but W1 plus W2 is less than minus W0. So it is contradicting, right? So that means you won't get a solution here. You will not get a solution. That means you cannot find a decision boundary in case of Excel problem. So this equation basically contradicts this and this. Fine. Yeah. So then, how to solve this problem? So, and I mean, okay, that's why actually you will learn something called as multi-layer perceptron in the next lecture, right? So how this perceptron actually is working? Let me just give you the idea behind it, how this perceptron learning algorithm works, and what are the steps to be followed here. Yeah. So yeah. So we are having here inputs for both the classes. One is like positive class, one is like negative class. I mean, the samples who are having level 1 is positive class and negative classes like samples are having class level 0. Right? So we have to initialize W randomly. As I mentioned, that you need to start with a random W and then we need to change the W value so that you will ultimately end up with a W for which you will get a better decision boundary, or we can, with that decision boundary, we can easily separate the samples of different classes. So this is what is the measure algorithm over here. While convergence, I mean till convergence, you have to repeat this process. What are those? You have to pick a random sample from the samples given to us, and if you need to check whether the sample is a positive sample or not. If it is a positive sample and the multiplication actually, I mean that is basically this one, the same equation, right? Wixi can be written in vector format in this way. W into X. X is a vector, W is a vector, it's just a dot product between two. Right? That means for positive class, if you remember, it should be greater than or equal to 0. Right? And that is correctly classified. We don't have to bother about this. But if the sample is positive and this equation, that means if it is negative, that means there is a misclassification. Right? If the sample is positive, but after multiplication, you are getting a less than value, I mean less than 0 value here. So that means it is a misclassification. So in that case, what you need to do is you need to just include, or you need to just add X into W. I'm just here there is actually a learning rate term, so I'm just ignoring that learning term, so that varies from 0 to 1. So you can just take it as 1. And if the X is a negative sample, and X can be a negative sample, and in that case, it has to be less than 0. But if you are getting greater than or equal to 0, that means again it is a misclassification. So then what you have to do and how to change the W value? Because it is a misclassification, I have to change the value. So how can I change the value? It is just, I have to subtract X from W. You have to repeat these procedures for till the convergence. Convergence means till all samples are correctly classified. What does it mean? So always you will not find these cases. That means for every positive class, you will get greater than or equal to 0 condition. And for every negative class samples, you will get less than 0. You will not get this kind of misclassifications. So now, how this actually addition and subtraction is helping, right, in modifying the W values, that is also very, very interesting to understand. Fine. So let us first talk about what will be the angle between, right? A little bit of mathematics is required to understand this, how actually this W plus X is going to help us here, and why this W minus X is help us, right? In case of misclassifications of positive samples as well as negative samples. It's very easy to understand. So what we are interested in here is again find out the line, the decision boundary, which separates the input space into two halves, right? And the equation is here like W transpose X equal to 0. This is the equation of the line. That is W1 plus X1 plus W2 plus X2 and so on up to Wn plus Xn. Right? So every point lying on this particular equation, right, satisfies this equation, obviously. And if I ask you what is the angle between this W and X, so you will definitely say, yes, the angle is 90 degrees. Because W is actually perpendicular to every point on this line. Right? So the angle is 90 degrees here. If I want to find out the angle between X and W, I mean W with any point on the line. that is 90 degree. Very, very important, right? So now we'll see if the sample is a positive sample, and if the sample is a positive sample, what will be the angle between W and X in that case? What will be the angle between W and X if it is a positive sample? If it is a positive sample, what will be the angle between W and X? And if it is a negative sample, if X belongs to a negative sample, then what will be the angle between W and that particular X? I've just written the answers over here. It should be less than 90 degree, or it will be greater than 90 degree. So how do you verify this? So let us again consider the formula which we have studied in our college level mathematics, that cos alpha is equal to W transpose X, right? This is a dot product is equal to, right, the magnitude of W into magnitude of Y. This is what we have learned from our college level mathematics, right? A dot product can be written in this way. So I can just write cos alpha is equal to W transpose of this. Right? I'm not considering this term, right? I am only considering this cos alpha is proportional to this term, the numerator, which is given to us, W transpose X. Right? If W transpose X greater than 0, what does it mean? These are positive samples. I hope you are agreeing with me. And if W transpose X is less than 0, these are negative samples. This is what we have seen, right, from the rules of these perceptrons. In this case, if it is greater than 0, that means I can say this cos alpha is also, because cos alpha is proportional to this term, I can say cos alpha is also greater than 0. So cos alpha is greater than 0, I can say alpha is less than 90 degree. Right? So alpha is less than 90 degree means the angle between W and X is always less than 90 degree. Right? If it belongs to a positive sample, so the angle should be always less than 90 degree. And if it is a negative sample, right, you can find out the alpha will be greater than 90 degree. But in these cases of misclassifications, what you will get in case of positive sample, the angle should be less than 90 degree, but what you are getting is greater than 90. So what you have to make, you have to just reduce the degree from, especially, right, you have to reduce especially the angle, right, from greater than 90 towards the less than 90. And that is where actually we're adding X here. And adding X will help us in reducing the degree, especially the angle between W and X from greater than 90 degree to less than 90 degree. If you want, you can also prove it. If you want, you can also prove it. Okay. Yeah, this is how we can prove it. You can see over here. Yeah. So what we are doing here, so in case of negative sample, I mean positive samples, if it is less than 0, right? So that means if it is a positive sample and it is less than 0, that means it should be actually the angle between W and X should be less than 90, but actually it is greater than 90. So that's why we are just adding like X to W. That means the new W is going to be W plus X. And the new angle is going to be, let's say, alpha nu. I'm just giving different notations over here. So cos alpha nu will be proportional to, obviously, because we know cos alpha is proportional to W transpose X. So in this case, cos alpha nu will be proportional to W transpose nu into X. So what is W nu? W nu is W plus X. So you'll be having two terms. So this is a positive term, right? X transpose X is a kind of X square term. So cos alpha is proportional to, cos alpha nu is proportional to cos alpha. Cos alpha with a positive term here, right? With a positive term. So that means which one is greater? So this one is greater, right? So if it is greater, so then the alpha nu will be less than alpha. This is a simple idea actually, I mean, which you can easily understand that yes, alpha nu will be less than alpha, right? That means previously it was greater than 90 degree, but it should be less than 90 degree. And that is why we're trying to add X. Adding X is helping us in reducing the angle between W and X. I hope you got my point, right? So you can see over here, yes, finally, actually, you will be having, so this was actually, let's say the W, right? Originally given to us. These are some of the positive samples. These are positive samples, you can see, and these are negative samples. And if let's say this is W, and if you find out the angle between W and the positive samples, it is greater than 90, which would be less than 90, right? And then, and it should be also for the with the negative samples, the angle should be greater than 90, but it is now less than 90. So what you have to do, that you have to change the W value repeatedly till convergence. So finally, I will end up with this kind of W, right? For which you will get a line like this. Right? So what is this line? This line is actually W transpose X equal to 0, where bias is already included with W. Right? So this is the final weight vector, for which if you see, if you now find out the weight, I mean the angle between this weight with the positive samples, it is less than 90, you see, and with the negative samples, it is greater than 90. Fine. And this is the line. If you draw this line, you can easily separate the positive samples and the negative samples. Right? But yes, perceptron can deal with the continuous values, although it is associated, although the input is associated with the weights, but cannot solve nonlinear problems. For the nonlinear problems, if you want to apply this algorithm, you will not end up with a solution. You will not get such a W vector for which all samples are correctly classified, right? So your algorithm is not going to converge in case of nonlinear problems. Right? You have to deal with some errors. You have to live with some errors if you want to deal with, if you want to deal with the nonlinear problems with the help of the perceptron algorithms. Right? So I hope at least you got some idea behind this, and maybe in the next lecture, you will learn what do you mean by multi-layer perceptron, why there is a need of multiple number of neurons, especially sigmoid neurons, right, to solve right nonlinear problems. So I was just showing you a single neuron can solve linear problems or linearly separable problems. Only a single MP neuron or a single MP neurons where x takes 0 and 1 values, and here x1, x2, x3 takes continuous values along with the weights, can solve linear problems. Right? You can solve many problems with this perceptron, but if it is only linear, if it is non-linear, you cannot solve using perceptron. Okay. So I will stop here. So if you're having any doubt, then you can write it in the chat box. I'll happy to answer.
Thank you so much, sir. I think you have covered most of the basics that was required for MLP, the motivation behind the MLP, and hope participants have understood all the concepts. It was a little bit mathematics, but it was a concept that is required to basically reason out why we are going with the multi-layer perceptron. And once we knew about the discriminant analysis, discriminant function, perceptron function, definitely getting the concepts of the next lectures will be very much easier for you. So I hope the basic foundations are clear for this from these two lectures. And if you have any query, you may ask, sir. Already the time is exhausted. So anyway, if you have a query, you may just ask quickly. And thank you so much, sir.
Yeah, thank you, Dr. Vikas, for the invitation and for the opportunity. I hope I could able to cover actually the fundamental concepts which are required to understand the further concepts of deep learning, right?
Yes,
So,
sir. Actually, I was also following the whole topic. It was actually means you have explained it in the best way so that it can set a motivation for the next lectures.
yeah, thank you. Thank you.
So participant, thank you. If you don't have any query, we may close for the first half session. We will be again joining back for the next session at 5. So there we are starting with the MLP, multi-layer perceptron, as Deepak sir has already told you. The session will be taken by Dr. Nitin M. So hope you will be there on time. Thank you all the participants. Thank you so much, sir, for the insightful session.
Okay.
Thank you all.